Hello, in this video we're going to talk about the inverse function theorem, and a reference we'll be looking at is section 8 of Analysis on Manifolds by Munkres. So let's say that you have an open set in Rn, and suppose that you have a function f from A to Rn, and let's suppose, for simplicity, that it's C infinity. Now we know that for f to have a differentiable inverse, the derivative df of f must be non-singular. So what that means is, okay, let me write that down. If f has a differentiable inverse, then that implies that f composed with f inverse is the identity on Rn. And so when you look at the derivative, you get that the derivative of f at x, well, maybe I'll just say the derivative of f times the derivative of f inverse must be the identity matrix. And therefore, the derivative of f must be invertible. And we'll prove that, at least locally, that this condition that the derivative is invertible shows that f is locally one-to-one. That's essentially what the inverse function theorem says. Well, it will f will be locally one-to-one, and the inverse will be differentiable. I should say that. So, first of all, it is true that if the derivative is non-singular, then f is locally one-to-one. So the lemma is, let's say that A is open in Rn, let's say that f is a map of class C1. If the derivative of f at A is non-singular, in other words, if it's invertible, and this is a function from an open subset of Rn to Rn. So the derivative is an n by n matrix. If this is non-singular, then there exists some positive number alpha such that the absolute value, or I should say the norm, of f of x naught minus f of x1 is greater than or equal to alpha times the norm of x naught minus x1 for all x naught and x1 in some open cube centered at A. Well, in particular, this norm on the left is non-zero. So f is one-to-one on this cube. In particular, f is one-to-one on this open cube. So the punchline of this lemma is that the invertibility of the derivative implies that f is locally one-to-one. In other words, it's one-to-one on some open neighborhood of A. Okay, and I'm going to skip the proof of that. Let's go to the theorem. One of the theorems says the following. Well, it's actually says several things, but there's this one theorem that says that if A is open in Rn, and f is a continuous one-to-one function, and f is a function from A to Rn, if f is continuous and one-to-one, then the image of A is open, and the inverse function f inverse from f of A to A is continuous. So actually being continuous and one-to-one implies that it's what's called a homeomorphism. F is a homeomorphism. It has a continuous inverse. This theorem is sometimes called Brouwer's theorem, the Brouwer theorem. Oops, spelled it wrong. The Brouwer theorem on invariance of domain. That's this part. It has nothing to do with differentiability. But if, in addition to the properties of the theorem, if in addition df of x is non-singular, if it's invertible for every x in A, then the inverse function I actually need this requirement of the smoothness of f. If in addition, okay, let's just put it here. If in addition f is of class CR, and again, we don't have to worry about this really, it's for the purposes of understanding the main theorems, we can just assume that f is of class C infinity. So if f is of class C infinity and df of x is non-singular for all x in A, then the inverse function f inverse from f of A to A is also of class CR. And well, that's if f is of class CR, but if f is of class C infinity, then its inverse is also of class C infinity. Okay. And this leads us to the inverse function theorem. So again, we have A is an open set in Rn, and f is a function of class CR. And f is a function from A to Rn. If df of x is non-singular for all A in A, then there is a neighborhood U of A. Maybe I'll just remove the vector sign. So there's the neighborhood U of A such that F carries U in a one-to-one fashion onto an open set V of Rn. Well, the set V is just going to be f of A, right? So this is just saying that F is a one-to-one map from U onto f of U.
I know we're clearing up in 15 minutes.
Okay, thank you. Such that, okay, so F maps U in a one-to-one fashion onto f of U, and the inverse function is of class CR. And again, if R is infinity, then the inverse function is of class C infinity. Okay. So what this is saying is that if the derivative is invertible at all points in the domain, then F is locally what's called a diffeomorphism. There's some, so here's A. Okay. So we're looking at R2, and F is a map from A to R2. Then the picture is that for every A here, there's some open neighborhood U such that F maps it. So here's f of A. And there's, when you look at the image of U under F, that's called V. Okay, that's f of U. That is an open set in Rn. We know that from the Brouwer theorem. And the inverse, which maps from V back onto U, is smooth. Let me just indicate that F is really mapping U onto V, right? I mean, it's mapping A to R2, but when you just restrict F to U, the image is V. And this is if the derivative of F is non-singular. Now, it's not true that F is globally one-to-one. Okay. So note, F in general will not be one-to-one on all of A. That's not surprising because we just have a restriction on the derivative, which is local, right? The partial derivatives, the matrix is non-singular. That we wouldn't expect would have such a strong result that F would be one-to-one. So for instance, if you take F from R2 to R2, which takes R theta to R cosine theta, R sine theta, then the derivative of F is going to be cosine theta, sine theta, negative R sine theta, R cosine theta. And the determinant is R. So if R is non-zero, this matrix is non-singular. But let's say that, so here's R and theta. Let's say that you look at the open interval from 0 to 1 to out to say B. So you look at the image of this open rectangle here. Well, when you apply f to that, that will give you a piece of the unit disk. Will it give you a piece of the unit disk? No, it'll give you a piece of the disk of radius r, right? And you'll get part of it. It goes out to the angle B. So if B is greater than 2 pi, then the image is, right? What happens is that the function f will not be 1-to-1, because if B is greater than 2 pi, then when you look at the image of this rectangle, I mean, the points go around the circle more than once. As you increase from 0 to B, right, the image is going to go out to B degrees, or B radians. So if B is greater than 2 pi, then f is not 1-to-1. Even though the derivative is non-singular at all points in the domain. Okay, so that's the inverse function theorem. So it says that if you have this restriction, so you have a map from an open set of Rn to Rn, and you have this restriction that the derivative is non-singular at all points, then not only is f locally 1-to-1, but the mapping is locally what's called a diffeomorphism. It's if f is of class CR, then the inverse is also of class CR. Okay, and that summarizes the statements of section 8 in Muncrist's analysis on manifolds. Thanks.